All right, we have to talk a little bit about chemistry, and I have to remind you of some of the things that I talked about at the beginning of the very first chapter. I had talked about how atoms have three primary subatomic particles, and I'd said the proton, the number of protons determines who you are, your identity. And then we had said you have the same number of electrons, these contain energy and are orbiting the same number as the protons. And these electrons are orbiting around the nucleus. And then, in addition to those two particles, we have another particle called a neutron. Now, electrons are tiny compared to protons. Neutrons are about the same size as the proton. So in the nucleus, we have the protons that determine the identity of an element and these things called neutrons, and together they're going to come up with the most of the atomic weight. So the electrons are only 1/2000th. Each electron is 1/2000th the mass of a proton. So when you think about the mass of an atom, even if you have 238 of those 1/2000ths, it's still not much. It's still, so most of the mass in, even if you, what am I saying, 238? Even if you have 92 of those electrons and they're 1/2000th of the mass of the protons, it still isn't much, right? It's still way less than a single proton. But we have the neutrons, and each one of them are big like a proton, and that's what I'm trying to say. So, when we look at uranium, we had said uranium is going to exist in two different isotopes. Now, what is an isotope? An isotope is an atom, or two different isotopes would be atoms with different numbers of neutrons. So, if you look at the uranium that is out there, we have two different forms. We have the uranium that has 146 neutrons, and so if you're a math type person, you'd say uranium has 92 protons. That's, if you are uranium, you have 92 protons. And then if you add to that 146 neutrons, that'll come up with, you will come up with 238 as the mass of that atom. Now, so one of the most common form of uranium has 146 neutrons. We have this other form of uranium that has three less. It has three less of these neutrons, and so 92 plus 143 gives us 235. Well, another point about isotopes is if you have what we call heavy isotopes, they're radioactive. And in the case of this U-235, it's going to be releasing neutrons. So what happens with uranium? We're getting back to our story, right? In the previous video, I talked about the researchers who somehow found barium. They said, what do we do? Where did this barium come from? We had uranium here. All we did is bombarded it with neutrons, and we ended up getting barium and this other compound. And we said this Meitner woman figured it out. And what did she figure out? She figured this business out. So let's take a look at this. This thing right here, this is that mass number. It's just like this or this. But then down here we have a zero. And so what it is, it's a neutron. It has mass, about the same amount as a proton, but it's not a proton, so it's got a zero down there. And we said, if you bombard this kind of uranium, this 235, uranium-235, with neutrons, if you bombard it with neutrons, it's going to absorb a neutron, for a very short period of time, and for a very, very short period of time becomes U-236. You see these brackets? That means it's very short-lived. It's highly reactive. It's not stable. So when that happens, it busts apart into these two compounds. And if you do the math, it all adds up, except that we release 3 neutrons. So U-235 is going to break apart, nuclear fission. That's what, and it's going to release neutrons. And what else does it release? A whole lot of energy. And so this is the basis of generating power with a nuclear power plant. Is we capture this energy, we convert the uranium, we break it apart with fission and release the excess energy. And then it's just like a coal-fired power plant. It produces a whole lot of steam, and the steam turns turbines, which produces electricity. All right.